A quantum computer tries every possible answer at the same time. That is the one thing almost everybody knows about these machines. And it is wrong. Not simplified. Wrong. And here is the good part. What they actually do is stranger, more beautiful, and it explains something the parallel answer story never could, which is why quantum computers are useless at almost everything. Let us start with the picture in your head, because it is a lovely picture. Say you want the best possible aeroplane wing. There are more shapes than you could ever test, so you load them all into 1,000 qubits at once, every design held in one machine, and you just let it check them all in parallel and tell you the winner. Simple, beautiful, completely broken. Because now you have to look at the answer, and looking is not a free action in quantum mechanics. The moment you measure that superposition, it collapses, and out comes exactly one result. One, chosen at random. So you fire up your unimaginable pile of wing designs, you measure, and the machine hands you the performance of one random wing. Congratulations! You have built the world's most expensive way to guess. This is the bit the parallel answers story quietly skips. A superposition is not a filing cabinet you can flip through. Every possibility really is in there, in some sense, but the exit door is one answer wide. Getting information back out is the hard part, and it is not a detail. It is the entire problem. So how does a quantum computer ever win anything? Stop thinking about computers and think about water. Drop 2 stones into a pond and watch where the ripples cross. In some places, a crest meets a crest, and the water leaps up higher than either wave alone. In others, a crest meets a trough, and the water goes completely flat. Not because nothing happened there, because 2 things happened, and they canceled. That word, canceled, is the whole video, because the numbers inside a quantum computer are not probabilities. They are amplitudes, and amplitudes are allowed to be negative. A probability of minus 30% is nonsense. A negative amplitude is Tuesday. And the instant your numbers can go negative, they can meet and undo each other and leave nothing behind. Watch how much that one ability buys you. A perfectly ordinary computer flipping coins also carries every possible outcome around at once as a giant list of probabilities. Nobody claims your weather forecast is running in a parallel universe. The difference is that probabilities can only ever pile up. They add. They are always positive. They can never, under any circumstance, subtract. Quantum amplitudes can subtract. That is it. That is the whole advantage. Which completely rewrites the job description. A quantum programmer is not writing a search. They are choreographing an interference pattern. The goal, in Scott Aronson's phrasing, is to arrange things so that for every wrong answer, the contributions to its amplitude cancel each other out, while for the right answer, they reinforce. You are not looking for the answer. You are building a machine in which every wrong answer flattens itself, so that when you finally look, there is only one thing left tall enough to see. And that is the actual magic. A quantum computer's power is not that it can check every answer. It is that it can make the wrong answers cancel out. It is not parallel search. It is noise cancellation, aimed at everything that is not the answer. Now, watch that one idea explain everything the myth could not. Start with speed. If a quantum computer really did check every option at once, searching a list would take a single step. It does not. The best known method, Grover's algorithm, takes about the square root of the number of items. Searching 1,000 or so needs roughly 80 goes. Faster than your laptop, yes, but 80 is not 1, and a square root is a very long way from magic. And square roots stop looking impressive fast. Go back to that unimaginable pile of wing designs. Grover's algorithm cuts the exponent in half, which sounds enormous, and still leaves you needing more steps than there are atoms in everything you can see. The speedup is real. It is also, for a genuinely gigantic pile of unsorted options, completely useless. Because cancellation is not free. You cannot flatten the wrong answers unless the problem has some structure to grab hold of, some pattern you can turn into an interference pattern. Shor's famous factoring algorithm does not try all the factors. It computes in superposition, then runs a quantum Fourier transform, which is an interference step, to pull out a hidden repeating rhythm. It works because factoring has a rhythm to exploit. Your spreadsheet does not. Your email does not. On almost everything you do all day, a quantum computer is not faster. It is worse. So what about the parallel universes? Honestly, that is one interpretation of the mathematics, not a description of the wiring, and it is nowhere near universally accepted. And notice that even if you granted it completely, the machine would be using all those universes in the single most wasteful way imaginable, borrowing infinite worlds and bringing back one random answer from one of them. The truth is so much better than the myth. A quantum computer is not a machine that tries everything. It is a machine that can subtract, and it wins by making being wrong cancel itself out. If you like the feeling of the world getting a little less mysterious, subscribe. One complex idea, made simple, every week.